Welcome. Today's notes worksheet is entitled Arithmetic Sequences and Series. And so now we're going to get pretty specific here, focusing on very particular types of numerical patterns. And so the first one that we're going to investigate is what's called arithmetic. So let's start it out. It looks like just at the top we'll put in a little definition, and then from there we'll investigate and see if we can come up with an explicit formula for it. So here's what I would say. Just if you can write this in as well, that would be great. We're going to talk a lot about what's called the common difference today. So the difference between any term and the preceding term is constant. So again, we will be referring to it as a common difference, our D value. And as a matter of fact, if you look at investigation 1 there, it kind of sets us up with an initial term. So the value of the first term is going to be 5. And what it is basically saying from there is that the common difference will be 4. So what does that mean? Well, let's kind of play it out and see if we can figure it out together. So anyway, just one more time, the difference between any term and the preceding term is constant. If that occurs, then you know that the pattern of numbers is what's called arithmetic. So everyone, I think what we're going to do is a 3-column approach for this. I have one column sort of in play right there. I'm going to do another column right here, and then a third column, how about right down there? And the second column, I guess what I'm thinking of is let's get specific with this and just start putting in our numbers. So let's start out. The value of the first term is definitely 5. And humor me for just a minute or two if you would, but in the third column, can you write another a sub 1 for me? Okay, now, first time is obviously the hardest. From there, this should become a piece of cake for us. But basically, the idea is that the common difference is going to be 4. Difference means subtraction. So based on our definition up above, it says take any term minus the previous term, and it will always be the same number, in this case 4. So we're asking ourselves basically is what minus 5 will give us that 4 right there. And I'm hoping you would see that this is going to be 9. So the difference between these two terms, for lack of a better description, is going to be 4. And so that's going to be 9 as a result. And I'm hoping just in terms of this piece that you see all I did is I took my first term and I added the difference. I added that numerical value of 4, and I got it. Okay, now let's run with it a little bit here. So the next one would be 13. And here's how we're going to write it. In this case, this is how I got the second term. To get the third term, it looks like I added another D. So I added another 4, which means up to this point, I've added 2 Ds. So I started at a sub 1, I added D to get to there, and I added another D to get to there. So I've added 2 so far. Okay, by the time the fourth term comes around, it looks like that would be 17. And in order to get that 17, I just took this term and added another D. So up to this point, it's 3 Ds. One more here, and then we'll see if we can pull it off. So that is definitely going to be 21. And I'm seeing that we added another D. So from the beginning, we've added 4 Ds. So take a look here. Inputs and outputs. And so the question, of course, becomes, after I do a little ... what's this? So how do I get the value of the nth term? What is the pattern that you see? So think about what would happen if I wanted the value of the 6th, the 7th, the 8th, etc. here. Look at what unfolded in our little table and see if you can come up with it. So let's put this just immediately in the blank right here. Notice it's bolded, and obviously we're going to be utilizing this, so please make note of this one. This is what's called an explicit formula because it's in terms of n. So explicit formula for the nth term of an arithmetic sequence. And so we've now had a little experience writing equations for the value of the nth term. So this would be a sub n equals, and here's what it looks like to me. We started with the value of our first term, a sub 1, and I kept adding d, and it looks like I'm 1 behind n. So when I did the 5th term, I've added 4 d's. If I wanted the 100th term, it looks like I would add 99 d's. And so in essence, I should get n minus 1 d's added onto that first term. And there you go. That's your first formula dealing with our focused sequences in series. All right, a sub n equals a sub 1 plus n minus 1 times d. Good. Let's utilize that with a few problems, and then we'll get into the series part to this lesson. Oh, I'm sorry. Actually, just one thing first here. Maybe just a little more in-depth look at this. It does say, what does the graph of an arithmetic sequence look like? Originally, I was thinking we would go ahead and make a little scatter plot out of this, but I don't think that's worthy of our time. So I'm going to go ahead and give you the sketch, and then we'll just kind of write it in. So if I made you do this, and it's sort of an input-output, n and a sub n, and actually plot those points. So the first term, so 1 and 5, 2 and 9, 3 and 13. Again, inputs and outputs. What we would basically see, everybody, is that it would form points on a line. It would look pretty much just like that piece right there. Now remember, sequences are unique compared to what we've seen before with all the other functions. Remember, I'm not going to go ahead and draw the line in place to connect the dots, because this is what's called a discrete function, meaning it's not continuous. I go from one point to another point, another point, another point, and another point. It just jumps from one to the next. So there's no continuity in between. So I guess for lack of a better description, let's just say points on a line, but not the line itself. Okay, now what type of expression is the formula? Well, of course, if we were to simplify this, now that we know it is linear in nature, obviously it's going to be a linear algebraic expression to produce it. So if we were to simplify it, and we will as we go through the process, well, very simply, we're going to get an mx plus b situation. And what does that difference represent? It's just another way, a different context for talking about the idea of slope. And so d represents the rate of change. How much does it change from one value to the next, to the next, to the next? A constant change means it's linear, and that change is represented by the slope. So I guess it says on your paper, what does d represent? I'm going to write it in quotes here because, you know, when we think of slope, we're talking about a continuous line. So I'll just kind of write it like slope, and then really it's the rate of change, the constant rate of change. It's changing by 4 for our investigation. Excellent. Good. So because it's slightly different here, we don't call this a linear sequence. We call it arithmetic. But in essence, it's basically the same. All right, so arithmetic is linear in nature. All right, well, let's do example 1. Be great for you to pause the video just for maybe about 30 seconds there and just decide each one. Is it arithmetic? And if so, what's your d value? All right, well, let's see. Again, just it has to go up or down by the same amount. That's what it means to be arithmetic. So the change has to be constant. And in this case, change is not constant, so it's a no. In this case, going down by 2, going down by 2, going down by 2. So the d is negative 2. Good. This one going up by 3, up by 4, up by 5, up by 6. Nope. The change is not constant, so it's not arithmetic. And that's all. Really just, is the rate of change consistent throughout your numbers? Okay. Let's go ahead and try example 2 now. So now just understanding that piece allows us to kind of formalize some of the patterns that we've already seen, and it takes some of the guesswork out, to be honest. So it just says find the 41st term of the sequence here, and I would look at this, and I know that you can sort of determine what's going on with that pattern of numbers. To represent it algebraically without having this particular formula might be a little difficult for us, but this, I think, it just simplifies it, in my opinion. So let's do this. Instead of the 41st term, for just a moment, because I think it just benefits us to really talk about and get used to the formula at hand, I'm hoping everybody sees that this is going down by 7 from one term to the next to the next. And so as a result, it is arithmetic. And the D value is -7. So rather than trying to match inputs and outputs, and by the way, don't write this on your paper, but rather than sort of playing guessing games and being, okay, how do I get from 1 to 11, 2 to 4, 3 to -3, 4 to 10, or -10, excuse me. Instead of playing those guessing games, now we just have to recognize it's arithmetic and utilize our formula. And the formula just basically says, start with the initial term, which is 11, and I just add n minus 1 d's to that first term. And so that's basically it right there. Now, if I asked you to simplify this out, and I will probably do so on the next example or two, we would distribute that -7 in, and you would see sort of that mx plus b unfold. But for right now, that's not what I'm after. So I just want the 41st term. And again, this was unnecessary, by the way, for this problem. I just wanted to illustrate that that's how easy it's going to be to write an algebraic representation for these arithmetic sequences. But the bottom line here is, if I want the 41st term, all I have to do is start with 11 and take 40 d's, so 41st term, so that means n minus 1 is 40, so 40 -7's on top of it. And just all you have to do is 11 plus, looks like -280, and there's my answer. So if I was to continue this out, 5th term, 6th term, 7th term, etc., all the way to the 41st term, I would be at about -269. Wonderful. All right, let's go to the next board. Okay, so 3 and 4 kind of go together here, and then 5 is a little added touch as well. So let's see example 3. It says write a simplified formula for the nth term of the sequence. And the good news is I gave you all the information you need. We're starting with 3, and I'm going up by 2's essentially. So let's get it started. And so in this case, I'm going to start with 3. Because it's arithmetic, all I have to do is start with my initial value and just keep adding n minus 1 d's on top of it. And that's it. That is your answer. It does say to write a simplified formula, and I guess the reason I want you to do that is so you can really see the connection to that mx plus b situation. So let's go ahead and distribute. If you don't mind, draw the arrows in here and here. And I've simplified that as well. I'm getting a 2n plus 1. Now this one's perfectly fine, of course. We utilized that on the last problem. When I wanted the 41st term, all I did is I made that 40 and went with it. But this works as well. You know, if I know n, here's my algebraic rule to get any particular value, to get the value of the nth term. Okay, that's it. Now it's going to get a little harder though. So we've got to find a way around this one right here. So in this case, unlike example 3 where I gave you all the good information, I gave you the value of the first term, I gave you d, I didn't give you much. So let's kind of play this out visually. I'm a very visual person, it kind of helps me. So this is the 8th term I see is 26. I'm going to lay it out this way. So the 8th term is 26. 9th term is unknown, 10th term is unknown, 11th term unknown, but the 12th term is 36. And so I do know for a fact that it has to go up by the same amount each time. And so I'm hoping that you would be in agreement with me that I think we can get the difference here. I think we can get the increase not per 4 values, but per value. So every time I go up by 1 in my pattern, what does the value of the term go up by? And as we've kind of talked about already, and this is where it comes into play, the difference that we're looking for is nothing more than slope. And do you remember how to find slope? Well, it's y2 minus y1 over x2 minus x1. Subtract the outputs on top and subtract the inputs down on the bottom. So it changes by 4 inputs and by 10 numbers over those 4 inputs. Changes from 26 to 36. And so you can see all I'm doing is just sort of finding the rate of change. And it looks like, again, 10/4. How does 2.5 sound? And so it basically is now saying it's going up by 2.5 each and every term in order to get from here to here. All right, that's great. Now we have a couple other things that we're going to need, and I'm curious how you want to go ahead and play out this last piece. We have D, but I don't have the first term, and that's what we need. We need A sub 1. And so we could think about this a couple different ways. I'm going to be formal about it and then maybe come back, although it's really the same idea, and maybe make it a little less formal as we go through. But here's, I guess, what I would say. We want the value of the first term. That's unknown. But what I do have, everybody, is a starting point, essentially. I have the 8th term, which is 26. Knowing that this is arithmetic will hopefully allow us to go ahead and use the formula in order to get the piece that's missing in the formula. I'm missing A sub 1. And so if I'm starting at 26, 26 is the 8th term, so this would be 8 minus 1, 2.5s. And so you can start to get a sense of what this is going to do mathematically, I'm hoping. And that's what we're going to do. We're just going to take 26 minus 7 times 2.5. And so when we do that, let me see if I have this piece. It looks like we end up getting 8.5 when all's said and done. So if I asked you to solve this equation, this product, whatever it may be, will get subtracted over. 26 minus that, I'm getting is 8.5. And that's perfect. That now allows us to go ahead and write our arithmetic formula, having A sub 1 and having D. And we would be able to write a formula for the nth term in this pattern. Okay, now this was, again, the very formal approach to this. Just looking at it up here, could you theoretically have just kept subtracting 2.5 until you get to this stage right here? And in fact, isn't that what I just did? I started at 26, and I took away 2.5. How many times to get to the first term? 7. And that's what you see from here to here. So you could have just said, all right, I'm going to take away 2.5 7 times, and that would give me the value of the first term, which we just found out was 8.5. Okay, now we're ready. So it looks like I started at 8.5, and I'm adding n minus 1 2.5s to it. Let's go ahead and distribute, everybody. So if I distribute there, I get my quote slope. There's your mx part, the difference, the independent variable, and what would be seriously the 0 term, but we don't think of it in those ways, would be just 6. All right, good. Let's leave that for now. That's good. That would be the final answer there. All right, we're doing just a bunch of examples to kind of solidify this formula so far. There's a secondary formula coming up momentarily, but let's do example 5 in the meantime. Nice one here, a little above and beyond. Let's see if we can work it out. It says, determine the value of x so that the terms are part of an arithmetic sequence, then find the value of each term. All right, so let's see. This, all I know, would be 3 terms in an arithmetic sequence. It doesn't matter if this is the first, second, and third term, or the 100th, 100th first, 100th second. It makes no difference. Just 3 terms in a row. Well, what is it that we know about this being arithmetic? Well, by definition, let's go back to that piece. By definition, any term minus the previous term is equal to that common difference. So when I see this, oops, I missed one thing on that. Let me just quickly fix that. So this would be a 3x plus 3. There we go. Okay, so this minus this, that's our difference. Well, it looks like I have one equation here with 2 variables. That's not good. But I look at the information and I think about this. This minus this also is that common difference. So that 4x minus 3 minus 2x plus 4, that's also equal to the common difference. I like that because it really reinforces that definition. Any term minus the previous term is constant. And so you can see, obviously, if each of these are equal to d, then they're equal to each other. And so let me find a little room to pull that off. I think I'm going to have to come over here. So I get 2x plus 4 minus 3x plus 3, and that equals 4x plus 3 minus 2x plus 4. All right, very good. And let's see what we want to do with this. Let's clean up a little bit on the left-hand side. 2x minus 3x is negative 1x. And 4 minus 3 looks to be a plus 1. Put my equals in place. 4x minus 2x. And notice, put parentheses with that subtraction there. Just be careful with that, of course. So I have a 2x, and then 3 minus the 4 should be that right there. Sounds good. I'm going to go ahead and bring that x over here and bring that 1 over here. I'm getting a 3x equals 2. And so x equals 2/3. Okay, good. So it did say, determine the value of x so that the terms are part of an arithmetic sequence. That would have to be the case. And if I plug them back in, and I'm just going to try to save ourselves a touch of time on this, you are more than welcome to do exactly this as well. But if you plug 2/3 back in here, 2/3 back in here, and 2/3 back in here, I believe you get 3 terms. I'm just going to go dot, dot, dot up until. I think you get 5 for the first one. You get 5 1/3 for the second one. And you get 5 2/3 for the third. And again, you are more than welcome to kind of check me on that. I didn't bring up my calculator. I just kind of looked at my sheet as I had done this one before. Put that in, and you get your 3 values. And you can see the difference here is 1/3. That's what makes it arithmetic. Excellent. All right, so 5 examples dealing with that particular formula. And it's time to try something else. That's the sequence component to this lesson. And now it's time to talk about the series component of our lesson. So remember, the only difference between a sequence and series, a sequence is just a pattern of numbers, whereas a series is the sum of that pattern of numbers. And so here, what we're going to do is an investigation or two. Looks like this would be the second one today, and this would be the third one on today's notes worksheet, to see if we can come up with our formula. So I'm hoping you sort of worked the formula with me as we had explored it on the original one, the explicit formula for the arithmetic sequence. Now, same premise. I want you to sort of think half a step ahead of me if you can, and see if you can come up with the formula right in here. So, arithmetic, nice and simple, everyone. I know you could all just expand this out, which, well, it's expanded. I know you could just go ahead and manually add those numbers together. That's not what I'm after here. I'm just wondering if we see a pattern. And so it says on your paper, do you see a pattern with what are called pair sums? And I guess here's what I would ask you to do. Try to visualize from the outside in, if you would. Outside in. And so start on the outside as a pair, and then work in as a pair. Next pair, 3 and 8. Next pair, 4 and 7. Next pair, 5 and 6. What do you notice about the pairs there if you were to add them together? Well, it looks like in each case, they're the same. So it says, do you see a pattern with pair sums? I would argue that the pair sums, well, let's write it this way, sorry. I would say that those pairs, let's be clear about this, add to 11. 1 and 10, 2 and 9, 3 and 8, 4 and 7, 5 and 6. All of those add to 11. How many of those pairs do you see? Well, it looks like there are 5. The 1 and 10, 2 and 9, 3 and 8, 4 and 7, 5 and 6. There are 5 total. And so if there are 5 11s, basically, from those pairs, then 5 times 11 equals 55. And if you were to do 1 plus 2 plus 3, etc., right down the line there, that's your sum. They add up to 55. And that, as a matter of fact, works for any arithmetic series. And so, let's see if we can do investigation 3, now obviously a little harder in terms of the numbers, but the pattern should hold, and it should allow us to come up with this sum. Again, I don't want to do it manually. I'm trying to find us a shortcut way to pull this off. So look at the pair sums, everybody. 5 and 40, 10 and 35, 15 and 25, and then I know there's an odd number here, but that's all right. Although, actually, I'm sorry. Oh, no, I missed it. 5 and 40, there we go, 10 and 35, sorry about that, 15 and 30, and 20 and 25. Finally got that. So it does look like the pair sum is going to be 45. How many pair sums are there? It looks like there are 4 of them. And so I've got 4 45s, and that's basically it. And 4 times 45 is 180. All right, so does everyone kind of see that? I'll connect them because I got lost. That's craziness. Got that, that, and that. 4 pair sums, all 45. And so 4 times 45 is 180. So now here's what we're going to do. The sum of the first n terms. Now just conceptually, I'm hoping you're okay with this. We're going to take this number and multiply it by the pair sums. So how many pair sums there are, and what is that pair sum? All right, well, how do we get the number of pair sums? If there are n terms, so in this case there were 8 terms, and obviously there were 4 pairs. So I'm hoping you would see that the number of terms divided by 2. So this gives me the number of pair sums. And that's what it did up here. 10 numbers, and there were 5 pair sums. Okay, so that's the first part. Now the second part is actually the pair sum. And as you can see, there are really different ways we can represent this, because you've got the first and last term, or the second and second to last term, or the third and third last term, etc., there. Usually it comes from these 2 guys right here, first and last. Because the first one, piece of cake, that's a sub 1. And the last term, of course, if I'm talking about n terms, would be a sub n. And there's your pair sum. So add up the first and last and multiply that by n over 2. Perfect. Okay, let's go try a couple out and round this out. So 6 and 7. So it says find the sum of 3, 8, 13, okay, all the way up to 53. So first and foremost is the recognition this is arithmetic. Does everyone see that? It's going up by 5s. The problem is I have a whole bunch of blanks in here before I get to the 53, so I can't really count it out. I know that's the first term. I know that's the second. I know that's the third. I have no idea how many terms into the pattern we are at this stage. So I think we have to find that first. Because, and I'm just going to get this going over here for a moment, I want the sum of the first, well, I don't even know how many terms. So it's going to be tough for me to utilize the formula if I don't even know how many terms I'm going to add together. So let's go for it and figure out how many terms there are. And I guess it comes down to the fact that this is arithmetic. It is still a pattern of numbers, where this is how we represent an arithmetic pattern of numbers. And I would argue we've got a good portion of that, and we just have to fill in what we have and solve for what we don't. All right, it looks like it's starting at 3. And I'm adding n minus 1 5s to this. And this is the nth term right here. I guess I'm going to put a little n and kind of equals right up there. I don't know what n equals when we get to that stage, but I know the value of the nth term is 53. I'm hoping everyone's all right with that piece, sort of what we did above. And so this is where I'm at right now, and this is what I started with, and the difference, I just don't know how many times I did it in order to get there. So everyone, how about we go ahead and divide by the 3? Just kind of thinking formally about this one. And that's the nice thing about that formula is I can just utilize it, put in what I know. And so how about divide by 5? Gives me 10. Oops. And just need to make sure I got that for you. So this is n minus 1. And then add the 1. And there we go. So this actually turned out to be the 11th term. So let's cross that out. And there we go. It's the 11th term. And so now I know I'm adding the first 11 terms together. And as a result, I take 11, divide by 2. By the way, questions have come up over the years in terms of that pair sum idea. Does it work with an odd number of terms? And it does. It does. The formula takes care of it. And so all I need to do is take 11 over 2 and then times the pair sum. First term, and in this case, the 11th term. And so if you get a chance, grab your calculator. This looks to be 5.5. So I have 5.5 pair sums. And it looks like the pair sum would be 56. My fault. And so when we do that, I get 308. Please check that out on yours. But the sum of the first 11 terms would be 308. All right. Good. So what I like about these problems is it requires a little thought. Yes, they're just formulas, and yes, we're just plugging numbers into the formula. But sometimes the things that we need in the formula are missing, and we need a way to go ahead and get it. And so you have to think strategically about it. Here, I utilized one formula to then get a part of a second formula. Wow, what a great problem. All right, let's wrap it up on 7. Find the sum of the first 1,000 odd numbers. So 1 plus 3 plus 5 plus 7, all the way down the line. So good news, I know how many terms I'm going to add together. Unlike the last problem, I'm going to add the first 1,000, which means I can start getting this going here. 1,000 terms divided by 2. And by the way, I should have said this up front. Is everyone okay with this piece? Dot, 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 all the way up to the whatever the 1,000th term is there, which we don't know. Is everyone okay with this being arithmetic? So the odd numbers, of course, are going up by 2. The difference is 2. All right, now, of course, I have that first term. Here is definitely the dilemma. I'm going to just underline it, kind of. Do I know the 1,000th term at this stage? No. And so what I need to do is find a way to get that 1,000th term. And so these formulas obviously work nicely together. This is the value of the 1,000th term, which I don't know, but there's a formula that allows me to get it. It's arithmetic, so which means I start with 1, and I add 999 2's. Everyone okay with that? So n minus 1, so 999 times, I'll add 2. And you can see that here. For the second term, I added 2 once. For the third term, I added 2 twice. Add another 2, add another 2, add another 2. Add it 999 times, and I'll get this. If you happen to grab your calculator there, I happen to have this, so I get 1,999. So that is the last term in our series. And you can see, of course, then what our pair sum would be. It looks like 2,000s all the way through. And how many 2,000s would there be? It looks like 500 pairs. So anyway, if you multiply this times this, I've got this one, 500 times 2,000. I'm getting 1,000,000, just kind of thinking about it there. And that would be it. So the first 1,000 odd numbers adds up to 1,000,000. Great. So arithmetic, sequences and series. Series just means it's a sum. All right, and they work beautifully in conjunction together. All right, so lots of formulas that you'll see. Try to know them pretty well, and the more practice you get with them, the more automatic it'll be. Well, thanks for listening, of course. Let me know if you have any questions.